Okay, so in this next short video, I just would like to give you kind of an introduction on how to solve this first one, because this first one is actually the most complex one. The ones to follow are more or easier to apply the rules of sum of the forces equals ma and sum of the torques equals I alpha. So anyway, let's calculate the acceleration of a marble of radius r as it rolls down an inclined plane pitched at angle theta. So we're going to actually derive an expression, and the easiest to focus on the linear motion about the center of mass. Okay, so that's what that dot is right here. So there's our center of mass. So we know that the force of gravity is acting right there. We know that the normal force acts about it, and then we also know that there must be some frictional force going against it, some force F that is restricting its motion. So if we apply the second law, so I'm going to slide this down a little bit. If we apply the second law, if we sum our forces and set that equal to ma, I have, and I'll do this in a different color, I have two forces. And this is the same thing that we did when we talked about inclined plane. We have the weight parallel, and then we have the weight perpendicular. And both of these forces are not what's actually causing it to accelerate down. The weight perpendicular is equal to the normal force, and the weight parallel minus this frictional force, this force going against it, is what's equal to my ma. So I'm going to write that. The weight parallel minus, and I'll go back to my blue, minus that frictional force is equal to my ma. Now, the weight parallel is my mg sine theta, and that's minus that f, and that's equal to ma. Now, in terms of the angular motion, we have the sum of the torques is equal to I alpha, where the moment of inertia for a sphere rolling down an inclined plane, or really any sphere that is solid, is 2/5 mr squared. So I could substitute that in for my moment of inertia, and you can look at this from your notes from the other night on angular dynamics to look up the moment of inertia for a sphere, times alpha, and the torque. The only torque that's actually acting about, since these two are acting at the center of mass, is this force F, and it acts, and I'll draw it on this side so you get a better picture of it. It acts perpendicular to the radius of the sphere, and so I don't have to worry about the sign, and so it's that F times R. And if I solve this for F, I cross off one of those R's and one of those R's, because this is the radius of the circle, and that's the distance between the center of mass, okay, which is the pivot point. It's the axis of rotation and the force it's acting on. So here's what I'm going to do. I have, and I'll rewrite this here, I have this is equal to 2/5 mr alpha. Okay, and if I relate the acceleration here in terms of alpha, I know that a equals alpha times r. So what I'll do is I'll rewrite this as m, and then I'll substitute alpha r in for a, so m alpha r. I'm going to do another substitution, okay, and I'm going to write it down here. I'm going to plug this in for that force. So I'm going to rewrite this down. I'm going to slide this down a bit. I have mg sine theta minus my 2/5 mr alpha, and that's equal to m alpha r. Okay, so I did two things there. I substituted the alpha r in for a, and that's right here, and then I substituted the 2/5 mr alpha in for f. And if we look, we have an m in every term, okay, and if I add the 2/5 r alpha over, add the 2/5 r alpha, okay, so that cancels that out. So I have g sine theta equals alpha r plus 2/5 alpha r. So if I think of it like this, if this is 5/5 alpha r, which is just 1, so that's okay, plus 2/5 alpha r, this is equal to 7/5 alpha r. And if I solve for alpha first, I cross multiply by 5 and then divide by 7r. So I get alpha equals f 5/7 g sine theta, 5/7 over r. Now if I want to get a is equal to alpha times r. So I basically take this expression and multiply it by r. So I get 5/7 g sine theta divided by r, so that's my alpha, times my r. So the r's cancel out. So I just get 5/7 g sine theta. Now if I were to replace it with a hoop, okay, the thing that would change here is my moment of inertia for a hoop is actually just mr squared. So if I go back up to where I plug this in, all I would do is get rid of the 2/5. So I'm going to rewrite this line right here, but get rid of this 2/5. So I get mg sine theta minus mr squared alpha equals m alpha r. Okay? And I'm sorry, this is not alpha squared, r squared. That cancels out. So I'll get rid of that. So if I solve this for alpha, I get something very similar. Okay, and if I go to this step, it's going to be alpha r plus alpha r. And so I get 2 alpha r. And so instead of this 5/7, I end up getting, and you could work through the math of this, I end up getting a is equal to g sine theta divided by 2. So check my math on that. Okay. Now, if I'm trying to find the acceleration of the center of mass, well, I could use this for the hoop. I could use this right here. I have a equals g sine theta divided by 2. And this is 9.8 times sine of 30, if we assume this number right here, and then we divide it by 2. 9.8 sine of 30 is 1/2. So I get 4.9 divided by 2, so this gets me the 2 sig figs, 2.5 meters per second squared. Now the angular acceleration, a equals alpha r, so that gives us alpha equals a by r. I get 2.5 divided by the radius of 0.6, and that gets me a angular acceleration of 2.5 divided by, oh, I'm sorry, the r is 0.08. That's where I made a mistake. All right, so my r is 0.08. So now that gets me what I have written down here, 31 rad per second squared. The moment of inertia, well, that's just simply for the hoop. It's just mr squared. So the mass is 0.5, the r is 0.08, square that. I get 0.0032 kilogram meter squared. The torque on the cylinder, torque is equal to I alpha. Now that I have I and alpha, multiply those two, and I get 0.1 meter newtons. The force of friction, well, the torque is equal to F times R. Okay, that's what we did up here. So going all the way back up to here, the torque from that force of friction is F times R. So now that I know tau, F is equal to tau by R, so that gets me 0.2 newtons. And then the angular speed at the bottom, well, I know it starts off at rest, so I actually have the relationship omega squared equals omega naught squared plus 2a, alpha rather, change in omega. Change in theta. So if I want to get that angular speed at the bottom, well, this is 0. And so omega is equal to the square root of 2 alpha theta. When I can make the substitution that my delta x, the length of the ramp, is equal to theta r. So theta equals delta x over r. So this is radical 2 alpha delta x over r. And if I plug in those numbers, you should end up getting a speed of 22 rad per second. So that's a quick one. You guys are going to be working on the rest of these during class tomorrow. And if you have any further questions, we can address them on Thursday. All right, have a good night. Bye-bye.